Hi everyone, and thanks for joining this session. Immutable infrastructure is a model in which no updates, security patches, or configuration changes happen in place on production systems. If any change is needed, a new version of the architecture is built and deployed. And because changes aren't allowed in immutable infrastructure, you can be confident in the deployed system. I'm Gunnar Grosch, I am a developer advocate at AWS, and in this session we're going to dive deep into the topic to learn why immutable infrastructure is essential in cloud architecture. As per the dictionary, something that is immutable is something that's not capable or susceptible to change. So why does it matter? Before answering this question, let's take a look at immutability in programming languages, because the problem with mutability there is probably a lot more familiar to many of you. So I love many different programming languages, and Python is one of them. But mutability in Python can and often is a headache. So let's simply assign variables here. Something simple, and yet, as you can see in this example, in Python, if you assign a variable to another variable of a mutable data type, any changes are reflected by both variables. So the new variable bar is just an alias for foo. So let's do the same in Erlang now, or try to do, because you can't. Languages such as Erlang, Rust, Scala, Haskell, Clojure, and a few others, they offer immutable data structures and single assignment variables with the premise that immutability leads to better code, simpler to understand and easier to maintain. And at this point, you're probably wondering, why does immutability matter and what does it have to do with cloud architecture? Well, headaches. The immutable infrastructure paradigm comes from the same ideas behind immutability in programming language. It is the idea that your architecture doesn't change once it is deployed, and it saves you from headaches. So let's dive into it and look at traditional infrastructure first, so we can understand the issue with immutability here. Not so long ago, it was quite common for folks to brag about uptime. The problem, though, is that long periods of uptime often indicates potentially lethal problems because critical updates, either software or hardware, often require rebooting. So let me ask you this very simple question. Which of these two choices make you more anxious? First, rebooting a server that's been up for 16 years, or second, rebooting a server that's just been built? Well, I guess we answered the same thing. Just talking about rebooting a 16-year-old server, it gives me anxiety because I have no idea what's changed in the 16 years since its initial boot up. So how many undocumented hotfixes were done? Why was it never rebooted? Are there some hidden or magic dependencies? To me, that's really terrifying. Other common practice in traditional infrastructure is mutable deployments, meaning the deployment pipeline gets the code, fetches the dependency, builds the artifacts, and deploys them for every environment stage of the deployment pipeline. One build per environment. What you test and validate here isn't what you're going to end up deploying. Also, in traditional IT infrastructure, servers are typically updated and modified in place. We SSH into our servers, we install, we update or upgrade packages, we tweak, and we optimize configuration files. It goes something like this. You log in, you stop the app, you update the repositories, you do a library upgrade, you test sometimes, you debug often, and you restart the app, and then you hope for the best. And during that time, the system is often down, by the way. All of these were, and often still are, standard practices. Less common practice, though, is to document all of these changes. And interestingly, the processes like change management and ITIL, they've been created in the industry to try to solve the problems due to changes, but never address the root cause of these issues. And instead, they just slow things down. So in my opinion, the solution to mutability isn't process, but not doing changes in the first place. And with the cloud, it's becoming more and more easy. And even for more advanced architecture using multi-availability zones, auto-scaling groups, I've seen, and I guess I'm guilty to this myself, I'm used to SSH to fix and tune things up. So we say just a quick edit to the config file to save the weekend. And we promise that we'll document and automate the fix first thing Monday morning, but perhaps we never do. So I like to call this practice SSH love syndrome. These practices make servers mutable. They change after they are created. So besides giving you headaches, mutations also lead to configuration drifts, which happens when active configurations diverge from the initially approved and deployed configuration. One of the main challenges with configuration drifts is that they make it hard to just replace or debug things, making recovering from issues difficult. So, how many of your applications fetch dependencies from the internet during the build process, or even worse, at runtime? I've seen places where deploying to production meant first launching any instance, any since it could be a different AMI between different environments, then fetching the code from different repos, building it, replacing the artifacts in place, and finally rebooting the server. One step was probably missing though, and that is the pray step. I'm sure all of you are either smiling or horrified by the idea, but how about your pip and npm install? How about Docker build? What guarantees do you have that the dependencies you're installing, that they don't change between deployments? And what if you're deploying to multiple machines or multiple environments? Don't you believe that this can be a problem? So you can read how one programmer broke the internet by deleting a tiny piece of code, a blog post. And what happens if your code repository has issues when you deploy and you can't download your code when you need it? So installing dependencies at runtime is an attack vector for malicious code injection, and it renders autoscaling slow. And that deployment behavior, it's fragile at best, and it leads to deployment mistakes and frequent rollbacks. And that's just if you're lucky. Luckily, of course, there is a solution to this. And put simply, immutable infrastructure is a model in which no updates, security patches, or configuration changes happen in place on production systems. If any change is needed, a new version of the architecture is built and deployed into production. And this is not a new idea. In fact, the term immutable infrastructure, it was coined by Chad Fowler in this blog post. Trash your servers and burn your code, immutable infrastructure and disposable components. It was published in 2013. Since then, the idea has, rightfully so, gained popularity and followers, especially as systems have become more complex and more distributed. An immutable infrastructure means that if a server needs an update or a fix, new servers are deployed instead of updating the ones already used. Once it is deployed, we simply update the routing mechanism to route the traffic to the new version of the application. So deploying applications in immutable infrastructure should use the canary deployment pattern. Canary deployment is a technique used to reduce the risk of failure when new versions of applications enter production by creating a new environment with the latest version of the software. You then gradually roll out the change to a small subset of users and slowly making it available to everybody if no deployment errors are detected. So canary deployment is sometimes called a phased or an incremental rollout. And once the new version is deployed to all users, you can slowly decommission the old version. And this strategy minimizes the potential blast radius of failure, limiting the impact on customers. It is therefore a preferred version. And the benefit of Canary deployment is, of course, the near immediate rollback it gives you. But more importantly, you get fast and safer deployments with real production test data. The main challenge with Canary deployment is routing traffic to multiple versions of the application. So consider several routing or partitioning mechanisms: internal teams versus customers, paying customers versus non-paying customers, geographic-based routing, using feature flags, or perhaps even random. And by keeping Canary traffic selection random, most users aren't adversely affected at any time by potential bugs in the new version, and no single user is adversely affected all the time. So how do we do Canary deployments on AWS? Route 53, a DNS service, lets you use a weighted routing policy to split the traffic between the old and the new version of the software you're deploying. Weighted routing enables you to associate multiple resources with a single domain name or subdomain name and choose how much traffic is routed to each resource. It is particularly useful for Canary deployments. And to configure weighted routing for Canary deployments, you assign each record a relative weight that corresponds with how much traffic you want to send to each resource. So Route 53 sends traffic to a resource based on the weight that you assign to the record as a proportion of the total weight for all records. So in this example, the resource with a weight of 10 gets 10/100th of the traffic, so 10%, and the other resource gets 90%. If there's one inconvenience to using DNS, it is propagation time. So Amazon Route 53 is designed to propagate updates you make to your DNS records to its worldwide network of authoritative DNS servers within 60 seconds under normal conditions. However, caching DNS resolvers are outside of the control of Amazon Route 53 service, and you will cache your resource record sets according to their time to live, the TTL value. So watch out for the default TTL values and shorten them. The worst part is that some resolvers don't even respect that TTL. I guess that is why DNS is often found guilty in many outages. So this is what we call an old school method, and one we used in production for many years, rolling deployments for autoscaling. And the basic version of that pattern needs at least two autoscaling groups behind a load balancer. You can then update one of the two autoscaling groups with the new golden image, V2 here, incorporating the latest version of the software and replacing the current instance with a new one using a rolling update. So rolling updates launch the new instance first, and once healthy with the load balancer, it drains the connections with the old instances and terminates them progressively. It is therefore a safe deployment method and with no downtime. For example, App V2 is the Canary with 1/4 of the traffic. You can then slowly increase the number of instances in that second group and progressively reduce the number of instances in the first autoscaling group. And this method is easy to automate since CloudFormation supports the update policy attribute for autoscaling groups with the autoscaling rolling update policy. AWS launched weighted target groups for application load balancer, which lets you control the traffic distribution between multiple versions of an application. So when you create an application load balancer, you create one or more listeners and configure listener rules to direct the traffic to one target group. A target group tells a load balancer where to direct traffic to, for instance, EC2 instances, Lambda functions, and so on. And to do canary deployment, you can use forward actions to route requests to one or more target groups. If you specify multiple target groups for forward action, you must specify a weight for each target group. For example, if you specify 2 target groups, one with a weight of 10 and the other with a weight of 100, the target group with a weight of 100 receives 10 times more requests as the other target group. If you require session stickiness, you can enable target group stickiness for a particular rule. When the application load balancer received the first request, it generates a cookie that encodes information about the selected target group, encrypts the cookie, and includes that cookie in the response to the client. So the client then needs to add that cookie in subsequent requests to the application load balancer. So for your serverless applications, you have the option of using Amazon API Gateway since it supports Canary release deployments. You can set the percentage of API requests that are handled by the new API deployments to a stage. When Canary settings are enabled for a stage, API Gateway will generate a new CloudWatch logs group and CloudWatch metrics for the requests handled by the Canary deployment API. You can use these metrics to monitor the performance and the errors of the new API and then react to them. You can then gradually increase the percentage of requests handled by the new API deployment or roll back if errors are detected. Note that currently API Gateway Canary deployments only work for REST APIs, not the new HTTP APIs. Finally, with AWS Lambda alias traffic shifting, you can implement Canary deployments of Lambda functions. Simply update the version weights on a particular alias, and the traffic will be routed to the new function versions based on the specified weight. So you can easily monitor the health of that new version using CloudWatch metrics for that specific alias and roll back if errors are detected. So changing aliases weights and checking the behavior of the newly deployed functions should of course be automated. Fortunately, AWS Code Deploy can help as it can automatically update function alias weights based on a predefined set of preferences and automatically roll back if needed. So to start using AWS Lambda alias traffic shifting with Code Deploy in just a few lines of code, you can check out the AWS SAM integration. So out of the box, they give you automatic alias creation, gradual shifting of traffic with rollback if needed, pre-traffic and post-traffic test functions to verify if the deployment is successful, and CloudWatch alarm integrations. So let's have a look at that in a demo. So let's do an AWS Lambda traffic shifting with the help of AWS Code Deploy. And we're going to do that using the AWS SAM framework. So let's look at that demo.
Our sample application is a basic AWS SAM application, a simple hello world. This is template for our application. It mainly consists of one AWS Lambda function, and that Lambda function is a hello world app. So let's open up the Lambda function code. And as you can see, one basic handler, which then returns a response with a hello world message each time it's invoked. So let's try it out by simply curling the URL for our API. And yes, it returns a hello world message for us. So switching back to the template. So these were the properties for our hello world function. And we are setting a live alias for our Lambda function. So let's switch something in the code. Let's make a change to hello demo instead, save that. And now let's deploy this application using SAM build and SAM deploy. So this will then build our serverless application and then deploy it. And as this is a demo of doing deployments using safe methods, we are using AWS Code Deploy to do a linear deployment 10% of the new version every 1 minute. We've also set up a pre-traffic hook, and the pre-traffic hook in this case, it is also an AWS Lambda function, which then allows us to test our new version of the Lambda function. So this is also defined in our template. So once again, a simple serverless AWS Lambda function, and that function will then run to verify the output of our new Lambda function. So it has an environment variable with the new version of our Hello World function. Let's look at the code quickly as well. This is the code for our pre-traffic Lambda function. We're using the AWS SDK to be able to update code deploy. We're starting our tests and then basically doing an invoke of our new version of the Hello World Lambda function. If there are errors, we will then return that error. If it succeeds, we will return that response. If there is 400 error code on the Lambda invocation, we will then say that the validation has failed. And then basically update our code deployment using that. So if it fails, we will update code the deployment, or if it succeeds, we will update so the deployment can proceed. Right, back to the template. Besides having that pre-traffic hook, we've also set up 2 alarms for our Lambda function. An alias on error metrics and on the new version. So these are also defined in our SAM template. So the first one is error metrics on our alias version, so the Hello World function that is live. And then we have an alarm set up for the latest version, that is the new version of our Hello World function. So it will monitor our Lambda function, and if there are alarms, they will then be triggered in AWS CloudWatch. So that's the basic setup. If we now check our deployment progress, we can see that the code deploy deployment has started. So let's switch over to AWS Code Deploy to have a look there. Just refreshing. All right, so we have a new deployment in progress. And this is then the new version of our AWS Lambda function. And as we can see, the pre-deployment validation, that's our pre-traffic hook, it has succeeded. So the tests we had in our Lambda function succeeded. And we can also see that it has deployed the new version and started shifting traffic. So 30% of traffic has already shifted to the new version of the Lambda function. If we check the AWS Lambda console and check our Hello World function, we can see that we have new versions deployed. Version 5 was the one that was live, and then version 6 is the new version of our application. And checking under aliases, we can see that version 6 right now receives 40% of traffic and version 5, 60% of traffic. So that's all updated using code deploy. All right, so let's try our function then. So once again, calling the API using curl. Hello demo, the new version. Hello world, the old version. Hello world, hello world, hello demo, hello demo. All right, so as you can see, we're receiving both the new and the old version when calling the API. which is intended as we're shifting traffic towards the new version. So if the pre-deployment validation hadn't succeeded, it would have stopped the deployment straight away. We're also able to stop and roll back deployment manually using the button in the console or using the APIs or the CLI. But since we have alarms set up in CloudWatch, we can also make use of those. So let's just try what happens if an alarm is set off. They are both in the OK state now, but we can use the CLI to set the alarm state of our CloudWatch alarms. So let's set the alarm state of one of these alarms into the alarm state instead of the OK state as now. So send that command using the AWS CLI. Let's update. In CloudWatch, we can see one is now in an alarm state. Switching back to code deploy, straight away we can see that the deployment is cancelled, and that is since an alarm was triggered. So now AWS code deploy switches 100% of traffic back to the original function. If we check in the Lambda console, we can see that version 5, that is the old version, now receives 100% of traffic. And if we test it in the CLI using curl, we can see that we're getting hello world, hello world, hello world. So the old version.
So that was a demo of using AWS Lambda traffic shifting with AWS Code Deploy. And using AWS SAM to do that makes it very easy. So let's talk about security considerations. And I want to hit the nail on the head here. Mutability is one of the most critical attack vectors for cybercrimes. When a bad actor attacks a host, most of the time it will try to modify servers in some way. For example, changing configuration files, opening network ports, replacing binaries, modifying libraries, or injecting new code. So a change means the architecture is compromised and it should be isolated and replaced immediately. And that is really DevSecOps at its best. Detect, isolate, replace. So let's look at some event-driven patterns. Extended the idea to cloud operations, the immutability paradigm lets you monitor any authorized changes happening in the infrastructure. So event-driven automations is an important pattern for responding to changes. Leveraging this pattern lets your architecture react in response to events. So an event is a change in state or an update, or worse, a change in configuration. Remember our immutable pattern? So doing this on AWS clouds means detecting changes using AWS CloudTrail and AWS Config, alerting using SNS, remediating with AWS Lambda, and replacing with AWS CloudFormation. For example, here's a simple pattern that responds to a change in an S3 bucket configuration. And if a change event is triggered, reverts that change and reapplies a strict configuration. In this example, setting a bucket private after it was made public. Here's another simple pattern that responds to a change in security group configurations. And if a change event is triggered, reverts that change and then reapplies a strict configuration. In this example, denying access via SSH from any locations, the famous IP 0.0.0.0/0. And as you can see, the event-driven pattern is an extension of the immutability pattern, and it's something that you should put in your toolbox. So let's take a look at that demo example, how we can use event-driven automatic remediation by leveraging the services like AWS Config, AWS CloudTrail, and AWS Lambda.
My friend Adrian Hornsby has created an example of how we can use event-driven automatic remediation using AWS Lambda. So this is a basic CDK application. So I'm just going to walk you through what it actually deploys. So it starts off by setting up a role and a managed policy for AWS config. Then we create a configuration recorder for AWS config to be able to record the event changes. Setting up an S3 bucket, adding policies to that bucket. Then we're adding the config bucket to our resource policy. Creating a delivery channel for config. And also setting up a CloudTrail trail. Creating a managed rule for config, and also enabling the config recorder. And this is the pattern that triggers if there are changes in config compliant rules. Setting up an event bridge rule based on that event pattern. And also adding an AWS Lambda function. And the Lambda function is what will then revoke the SSH access in this case. And this is a basic Python AWS Lambda function. And it will then receive that event from EventBridge. And based on the content in that event, it will then allow us to revoke SSH access. So based on the security group in question, we will then be able to update the IP permissions and then basically revoke public access for that specific security group. So I have already deployed this CDK stack, and these are the resources that gets deployed. So we have everything regarding AWS config, we have our events rule, we have our AWS Lambda function. So looking in the config console, we can see that one rule is now set up. It is compliant as of now. We have a rule set up in EventBridge, and that rule consists of this event pattern. So when something is non-compliant, it will then target the AWS Lambda function and then disable SSH. So this is our target, the Lambda function. And as we can see in the Lambda console, we also have that Lambda function in place now, the code we looked at in VS Code before. So let's try it out. Let's then make a change to our default security group. I'm going to edit the inbound rules and add a new rule. And in this case, of course, going to select SSH and then allow it from anywhere and save this rule. All right, so I have pre-baked this example, so we can now switch to config and have a look. As you can see now, the resources in scope are now non-compliant. So this means that it would now invoke our AWS Lambda function. Let's see if it has invoked it. We can check under monitoring. And we can see that this Lambda function should now have been invoked once. Yes, successfully. So if we check the VPC console again and check our security group, let's refresh. The inbound rule that I added, inbound SSH from everywhere, is now removed. Meaning that our AWS config rule should now switch back to being compliant. No resources in scope.
So that was a great example of how we can use event-driven automatic remediation to, in this case, block access from anywhere to SSH by using AWS config and having an event-driven invocation of a Lambda function that then remediates that issue. So there are plenty of benefits to immutable architecture, so I want to walk you through some of them. So by frequently replacing servers from a base, known and version-controlled configuration, the infrastructure is reset to a known state. Avoiding configuration drifts, all configuration changes start with a verified and documented configuration push to the code repository, for instance a Git push. Since no changes are allowed on deployed servers, you can remove SSH access permanently. That prevents manual or undocumented hotfixes, resulting in complicated or hard to reproduce setups, which we know often lead to downtime. And deployments are simplified because they don't need to support upgrade scenarios. So upgrades are just new deployments. Of course, system upgrades in immutable infrastructure are slightly slower since any change requires a full redeploy, but the key here is pipeline automation. And deployments either complete successfully or nothing changes. It renders the deployment process more reliable and trustworthy, with no in-between states. Plus, it is a lot easier to comprehend. And deployments using canary patterns are safer because the previous working version isn't changed. You can roll to it if your deployment errors are detected and roll back. And additionally, since the same process to deploy the new version is used to roll back to older versions, it makes the deployment process safer. And since all servers are running a particular application use the same image, there are no differences between our different environments. One build deployed to multiple environments, and it prevents inconsistent environments and simplifies testing and debugging. And since servers use the same base image, they are consistent and repeatable. It makes autoscaling trivial to implement, significantly increasing your capacity to scale on demand. And the tool chain is simplified since you can get rid of configuration management tools, managing production software upgrades. So no extra tools or agents on servers. Changes are made to the base image, tested and rolled out. And by denying all changes to servers, you can disable SSH and remove shell access to servers. That reduces the attack vectors for bad actors, improving your organization's security postures. So, as I said, there are plenty of benefits. The most important to me are safer deployments and increased security. So, if you want to get some additional resources on architecture and your infrastructure, check out the AWS Well-Architected Framework, check out our AWS Architecture Center, use the AWS Well-Architected Labs, and take a look at our AWS Solutions Library, where we have vetted reference implementations and well-architected patterns available for you. So with that, I want to thank you all for watching. We've looked at how immutable infrastructures are more consistent, reliable, and predictable, and they simplify many aspects of software development and operations by preventing common issues related to mutability. If you have any questions or comments, do reach out on Twitter @GunnarGrosch or connect on LinkedIn. I'm happy to connect. Thank you very much for watching.